μαζί μας τον κορυφαίο θεωρητικό φυσικό John Ellis. Θα σας πω 2-3 πράγματα, αν και γνωρίζω ότι τα ξέρετε. Ο John Ellis είναι Βρετανός θεωρητικός φυσικός, καθηγητής θεωρητικής φυσικής της έδρας Maxwell στο King's College του Λονδίνου. Τα ερευνητικά του ενδιαφέροντα έχουν σχέση με τη σωματιδιακή φυσική και έχει συνεισφέρει σημαντικά στην αστροφυσική, στην κοσμολογία και στην κυβαντική βαρύτητα. Οι περισσότερες από τις δημοσιεύσεις του έχουν άμεση σχέση με τα πειράματα, την ερμηνεία των μετρήσεων και είναι ο κορυφαίος θεωρητικός φυσικός του ΣΕΡΝ. Έχει βραβευτεί, έχει πάρει πάρα πολλά βραβεία και έχουμε τη μεγάλη χαρά να σήμερα μαζί μας. Ένα χειροκρότημα. So we begin with questions about cosmology. Ξεκινάμε με ερωτήσεις κοσμολογίας. Άγγελε, είναι εσύ καλύτερα. Ας επέλεγε εσύ. Επέλεγε εσύ όποιο παιδί θέλεις. Κοσμολογία.
Cosmology. We start from front row.
How did the Big Bang start?
We don't know. What we know is that the universe is expanding, and I see you have a model out there of the expansion of the universe, and so we can sort of run that back towards the beginning. But if we try to go right back to the beginning, then the laws of physics that we understand break down, and so we can't tell what happened, if you like, when time was equal to zero, or what happened before the Big Bang started. Our laws just break down. This is something for you to solve in the future.
Θέλετε να μεταφράζω?
Θέλουμε να μεταφράσουμε.
Okay, they all...
Ναι, λίγο να
να πούμε λίγο την απάντηση έτσι πολύ γρήγορα. Δεν ξέρουμε. Δεν ξέρουμε τι έγινε στο σημείο 0. Στο χρόνο αυτό. Δεν ξέρουμε ίσως τι έχει γίνει πριν και αν έχει γίνει κάτι πριν. Δεν το γνωρίζουμε. Και είναι κάτι που ίσως εσείς θα θέλετε να ανακαλύψετε στο μέλλον. Δεύτερη ερώτηση.
If we find more matter, is there a chance to increase the 5%? 5%.
Okay, so the part of the universe that we understand, I think this is the 5% that you mean. This is matter that we see around us, the atoms, the molecules, and so on. And that's what's described on my T-shirt. Okay? Then there is something like 25%, which is what we call dark matter. So dark matter has gravity, like ordinary matter, but it does not shine. We don't see light, that's why we call it dark matter. So there are some theories that say that if it's made of particles, and those particles we can perhaps make with the Ellis, the Large Hadron Collider. So now we're doing experiments to look for the possible particles of dark matter. But it could be that dark matter is something else. Or it could be that it's made of particles which are just too heavy to make with a Large Hadron Collider. We don't know.
Wow. Let's take the girl in the back.
After the Big Bang, the Higgs field gave mass to the universe. Does it still give mass to the universe today?
Yes. So what the Higgs field phi here, what it does is it gives masses to elementary particles. So the electron, for example, or the quarks that make up the proton, they get their masses from the Higgs field. Now, early in the universe, the Higgs field was not there. The Higgs field was just a particle like any other particle. And I like to compare it to a field of snow. When the universe was very, very hot, the snow, the Higgs snow, could not settle on the ground. and particles just ran around without any mass. Then when the universe cooled down, it's as if the snow could then settle on the ground, and then when particles try to go through this field of snow, then they acquire a mass. And that's where we are now. But this big snow started settling on the ground when the universe was about a millionth of a second old.
Για να το πούμε λίγο αυτό και στα ελληνικά, για να το καταλάβω. Όταν ήταν το σύμπαν πάρα πολύ, ήταν ένα βρέφος, έτσι, είπε πριν 1/1000 του εκατομμυριουστού του δευτερολέπτου. Φανταστείτε. Πριν από αυτή τη στιγμή ήταν σαν μια χιονοθύελα. Ήταν μια χιονοθύελα. Μετά όμως αυτό το χιόνι έκατσε και έγινε ένα χιονισμένο τοπίο. Φανταστείτε μια πολύ μεγάλη πλαγιά. Εκείνη τη στιγμή, λίγο δηλαδή μετά από το 1/1000 του εκατομμυριουστού του δευτερολέπτου, μπορούμε να πούμε ότι το πεδίο Higgs ήταν σε ένα χιονισμένο τοπίο, οπότε σιγά σιγά τα σωματίδια εκείνη τη στιγμή αρχίσανε και αλληλεπιδρούσαν με το χιονισμένο τοπίο. Άλλη ερώτηση. Πάμε από εδώ, let's go from, I can't choose, you.
Why was the universe hot in the beginning and now it is cold?
I think the honest answer is that we don't know. So we know that the universe is expanding. We know that as it expands, it gets cooler, it gets colder. I don't know, maybe you can do experiments that show that when you have a gas, it starts off very hot, tense and compressed. And then if you expand the gas very suddenly, it gets colder. So this is a law of physics that we understand very well. But what we don't understand is why it started off so hot and so dense.
How do we know that we have only discovered 5% of the matter in the universe?
So there's various ways that we have of figuring out how much of the universe is visible matter that we can see around us. So, for example, we can measure the number of stars, we can measure the dust that is in galaxies, and from that we know that there is some percentage, but there must be other stuff as well, dark matter, to hold the galaxies together. But then we can also look back towards the beginning of the universe, and for example, the universe is full of radiation, particles of light, which started very early in the Big Bang, about 300,000 years after it started. And by measuring the properties of that light coming from outer space, we can again measure the amount of ordinary matter in the universe, and we come up with the same number. And we can measure the numbers of different elements, by light elements like helium, for example. And that also tells us how much ordinary matter there was in the universe, right back at the beginning. So we've got many different ways of measuring the amount of ordinary matter in the universe, and always we get the answer 5%.
Να μεταφράσω ότι η ερώτηση ήταν για το 5%, γιατί είναι 5% η ύλη του σύμπαντος, και η απάντηση είναι ότι έχει υπολογιστεί από τη μάζα των γαλαξιών, από το φως, και τι άλλο είπε?
Από την αστρική σκόνη, από το ήλιο, το οποίο υπάρχει στο σύμπαν, και επίσης και από τα αστέρια. Δηλαδή όλες τις πληροφορίες που παίρνουμε με διαφορούς τρόπους μετρήσεων μας δίνουν συνεχώς ότι όντως είναι 5%. Αυτό το οποίο η ορατή ύλη, δεν μιλάω για άλλη ερώτηση. Okay.
Since inside the problem there are two kinds of parts.
Όχι, κοσμολογία. Cosmology.
Cosmology.
And then, yes, and then we will...
So, guys, stick to cosmology, You?
What do you think will happen if the universe stops expanding?
So at the moment, the universe is not just expanding, but the expansion is accelerating. So something would have to change if the universe were to stop expanding. So this is possible. So we talked about the ordinary matter, we talked about dark matter. There's something else in the universe that we call dark energy. And this dark energy is, even in empty space, even where there's no particles, no matter, there is some density of energy there. And this is a puzzle. We don't understand this dark energy. If this dark energy stays, the universe will continue expanding and its expansion will accelerate. But we don't know. Maybe the dark energy will disappear at some point. Personally, I don't think so, but it might. And if it does, then the universe perhaps might stop its expansion and even contract in what we call a big crunch. But we don't know. There's no evidence that that's going to happen.
Θα πούμε λίγο αυτή μια μορφή, ότι ο καθηγητής πιστεύει ότι, προσωπικά πιστεύει ότι το σύμπαν θα συνεχίσει να διαστέλλεται και μάλιστα επιταχυνόμενο. Και επίσης μίλησε για την υπεύθυνη ενέργεια, έτσι, για την ενέργεια που είναι υπεύθυνη, τη λεγόμενη σκοτεινή ενέργεια. Δεν ξέρουμε τίποτα για αυτή την ενέργεια, δεν ξέρουμε τίποτα για τις ιδιότητές της, για το πώς συμπεριφέρεται, για το πώς αλληλεπιδρά με την ορατή ύλη, ίσως και με τη σκοτεινή ύλη. Αυτό το οποίο όμως έχουμε παρατηρήσει ότι αυτή η σκοτεινή ενέργεια είναι υπεύθυνη για την επιταχυνόμενη διαστολή του σύμπαντος. Αν αυτή η ενέργεια πάψει να υπάρχει, έτσι το γνωρίζουμε, τότε υπάρχει ίσως μια θεωρητική πιθανότητα, ακόμα δεν έχει αποδειχθεί με κάποιο πείραμα, ότι το σύμπαν όντως μπορεί να σταματήσει να διαστέλλεται. Αλλά ακόμα δεν το γνωρίζουμε.
Και να καταρρεύσει το Big Crunch. Η πέμπτη περίπτωση που σας είχα πει.
Αλλά μην φοβάστε, don't be afraid of
Big Crunch.
Donald Trump get us first.
Αλλάζουμε για το CERN.
Okay.
So the question is about
It's about CERN.
CERN. Yes.
In what way will the Higgs, what things will the Higgs boson help us?
In what way will the Higgs boson help us? I don't know. So all that I can say is that in the past, every time we discovered something new about the universe, it turned out to be useful to something. So 1897, people discovered the electron. Now we have electronics. In 1905, Einstein said there has to be a particle of light, the photon. And now we have lasers, we have photonics, lots of applications. In the 1920s, Dirac said there had to be antimatter. And people thought antimatter is useless. But now antimatter is used in medical diagnosis. So sometimes it takes many years, but always in the past, a new scientific discovery has had some sort of application. So I have no idea what use the Higgs boson might be, but at least if we understand more about the universe, I think we can make some sort of technological advances.
Θέλετε να τα φτάσουμε? Όχι.
How do we grasp the Higgs boson?
How do we?
Grasp.
Okay. You mean how do we discover it, or how do we think about it? How do we discover it? Okay. So the way we do experiments in particle physics, as we know, is we collide particles. For example, at the Large Hadron Collider, the LHC, we collide protons, and we make them as energetic as possible. And then, with that energy, we can make new particles. So specifically with the LHC, we collide particles at something like 10,000 times the energy that a proton has when it's sitting at rest. So we can make heavy particles by converting that energy into the masses of other particles. Now, so you can produce lots of Higgs bosons. But then the question is, how do you see a Higgs boson? And the Higgs boson lives for a very, very short time. So it doesn't leave a track in your detector. In fact, it doesn't have an electric charge. So even if it did live for a long time, we wouldn't be able to see it. But what we can see is what it decays into. So sometimes it decays into charged particles, sometimes it decays into energetic photons, energetic light particles. And these we can detect. So I think we've got a model particle detector outside of the corridor. So these particle detectors are like onions with different layers, and each of those layers is looking for a particular type of particle coming out. So for example, there's a layer which is looking for photons, light particles. There's a layer on the outside which is looking for particles called muons. Have people heard of muons?
Yes.
Muons, okay. So on the outside there's a layer looking for muons. So what the two big experiments did, Atlas and CMS, is that they both looked for photons, they looked for muons, they looked for electrons. And they found extra events with photons or with muons or with electrons that they could not understand in terms of the physics that was known before. It had to be some sort of new physics. So they said, okay, we found a new particle. But then what you have to do is you have to study the properties of this new particle and check to see whether it's really a Higgs boson or not. So I like to think of it as you're doing a jigsaw puzzle and there's a piece that's missing, and you look everywhere for this piece of the puzzle, and eventually in the back of the sofa you find a bent piece of cardboard and you can't make out the picture, and you have to study it very hard and see whether it's the right size and shape to complete the jigsaw puzzle. And so this is what we were doing for 2 or 3 years after the discovery of the new particle. And then finally we said, well, no, we're now convinced that this really is the Higgs boson. Answer the question?
Λοιπόν, να κάνουμε μια μικρή μετάφραση και γρήγορη γι' αυτό, σε περίπτωση που το σωματίδιο Higgs είναι πάρα πολύ δύσκολο να το ανιχνεύσουμε, όπως έχει φτιάξει και τις μακέτες, το CMS, το Atlas, τους ανιχνευτές. Αυτοί οι ανιχνευτές είναι σαν τεράστια κρεμμύδια, όπως πολύ καλά ξέρετε, έχετε μελετήσει, με πολλά στρώματα που ανιχνεύουν διαφορετικά σωματίδια. Αλλά το Higgs boson, επειδή δεν έχει και ηλεκτρικό φορτίο, έτσι, και να το έβλεπα, δεν θα μπορούσα να το ανιχνεύσω. Και να ήξερα πού ήταν, δεν θα μπορούσα, γιατί δεν μπορεί να κάνει vent. Όμως τι κάνω, μπορώ να βρω την υπογραφή του. Οπότε η θεωρητική φυσική, όπως και ο καθηγητής και άλλοι, είχαν πει ότι το Higgs boson ζει πάρα πολύ λίγο. Βασικά ζει 10 στην 22 δευτερόλεπτα, έτσι, ούτε καν. Δηλαδή είναι αόρατο. Αλλά μπορώ να βρω τις υπογραφές του, πώς διασπάται αμέσως σε άλλα σωματίδια. Όπως είναι τα μειόνια, όπως είναι τα ηλεκτρόνια, μπορεί να είναι και φωτόνια. Έτσι. Οπότε τι είναι ένα μικρό κομματάκι του puzzle, όπως όλοι έχουμε χάσει κομματάκια puzzle πίσω στον καναπέ ή κάτω από το χαλί ή οτιδήποτε. Και λέμε πού είναι το τελευταίο κομματάκι του puzzle, το βρίσκω, έχει τσαλακωθεί, έχει σκιστεί λίγο κτλ. Οπότε μας παίρνει και λίγο ώρα να δούμε, είναι το κατάλληλο σχήμα, είναι το κατάλληλο χρώμα, είναι το κατάλληλο κομμάτι και πού θα μπει στο puzzle. Αυτό που έγινε στο ΣΕΜ και μετά το 2012. Γιατί δεν το βρήκανε και πήγανε για. Και αλλάξανε. Πρέπει να το μελετήσουν, να δουν τις ιδιότητες τους. Και έχει κάνει 2 χρόνια και τώρα λένε με αυτοπεποίθηση ότι ναι, όντως είναι το Higgs boson που ψάχναμε να δούμε. Yes.
Why is there radioactivity in CMS?
Why is there
Radioactivity.
So radioactivity can come from various different origins. So sometimes it's a nucleus that breaks up, Sometimes it's one type of nuclear particle changes into another. So I think you know that nuclei are made of neutrons and protons. So if you just have a neutron by itself, it's unstable. It breaks up, and that's one form of radioactivity. Another form of radioactivity is what you have sometimes with very heavy elements, which are made up of lots of protons and neutrons, and they just can't hold themselves together, and they break apart. That's another form of radioactivity. So what happens in the LHC is that we have the protons going around. The protons by themselves are not radioactive. But if a proton hits, for example, a piece of a detector, or if it hits part of the tube where the beams go, then it can make perhaps an unstable nucleus. And then you've got a form of radioactivity. Inside CMS, also you make lots of collisions, and those collisions produce lots of neutrons. And as I said, those neutrons are unstable, and eventually they decay with another form of radioactivity. But all that type of radioactivity goes away after a while. So the neutron, for example, lives for a few minutes and then changes into a proton, the proton is stable. So it's true that there's radioactivity in CMS, but most of it goes away when you stop operating the accelerator. So that is how physicists and engineers, after a period, can go back inside CMS and maybe fix something if something is wrong.
Okay, καταλάβαμε και το πώς... Τέλεια.
What will be discovered with the theory of sushi?
What do they discover?
Hold on, because we stick to certain questions. I mean, it's a professor, but my process is the next possibly stage. Do you have any other question regarding the LHC, the operation, the people, the scientists? Is there one?
Όχι, συγγνώμη.
Okay. Please?
I think we're having to get into physics. Yes. So we think we know how many quarks there are of the conventional type. So there's 6. Okay? But it's possible that there might be other things, perhaps not exactly quark, but things like quarks. And so in fact, right now we're thinking that maybe some other particles like that might exist. But there's no direct evidence at the moment. But well, perhaps later we'll discuss why people are excited at CERN at the moment. People think there may be new particles beyond the Higgs boson, and these might include more quarks. Not exactly the same as the quarks that we know about, but something similar.
Okay, I think that with this question we entered physics.
Yeah, I think so.
So let's continue.
Στοιχειώδη σωμάτια.
Now maybe we'll go back to the Suzy question.
Yeah, so who was the Suzy? Oh yes, go on.
What will be discovered with the theory of sushi?
Okay, so Suzy, maybe you know, that's an abbreviation for a theory called supersymmetry. It's called supersymmetry because symmetries relate different types of particles, and this is a type of symmetry that we've never seen in nature before. So it would certainly be very exciting if we discovered it. Sometimes it's more exciting to discover a new principle, a new symmetry, than to discover a new particle. So in this particular theory of supersymmetry, for every known particle, there is another particle which has the same properties like electric charge, but it's heavier and it spins in a different way. People heard about spin?
Spin? No.
No. Okay. Good. Something you guys don't know. So all the elementary particles you can think of as being like dancers, like ballerinas. And ballerinas, they do their pirouettes, they turn around like this. And so a photon is a particle of light. This turns around. The electron, that turns around, but more slowly. The Higgs boson, well, actually the Higgs boson is the one particle we know that does not turn around, has no spin. So particles of matter, like the quarks that we were just discussing, the electron, those all spin slowly. The particles of forces, like the photon, they will spin more quickly. And supersymmetries can, in principle, relate matter particles to force particles by relating particles to spinning in different ways. So this is all very nice and theoretical and mathematical and so on and so forth. But what use is it? Well, for example, the lightest supersymmetric particle could be the dark matter that we were talking about earlier on. And one of the things that Atlas and CMS are now doing is looking for events where these dark matter particles, the supersymmetric particles, might be produced. So you can't see a dark matter particle directly because it's dark, it doesn't shine. But it carries away energy, it carries away momentum, and so you look for events where there's some energy and momentum that escape from the detector which you weren't able to measure.
Στο θέλετε και μια μετάφραση? Ναι. He would like some translation about Susie. So, ξέρουμε ότι τα σωματίδια έχουν ηλεκτρικό φορτίο. Αυτό το οποίο μάθαμε όμως ότι έχουν και την ιδιοπεριστροφή, το οποίο στα ελληνικά το spin.
Συγχωρεύτηκες,
Φανταστείτε δηλαδή τα σωματίδια σαν χορευτές. Κάποια όπως το ηλεκτρόνι, το οποίο περιστρέφεται γύρω από τον εαυτό του, να κάνει πυρουέτα, σαν μια παλαρίνα. Κάποια περιστρέφονται πιο γρήγορα, κάποια λιγότερο γρήγορα. Το σωματίδιο Higgs δεν περιστρέφεται. Γιατί δεν έχει ίδιο περιστροφή. Ίδιο σε προβλήμα το spin. Τώρα, για τα υπερσυμμετρικά σωματίδια, τα οποία ψάχνουμε να βρούμε, αφού βρήκαμε το Higgs, να βρούμε το Atlas και το CMS, και ψάχνουμε τώρα, θεωρείται ότι είναι βαρύτερα, με μεγαλύτερη μάζα και με πιο ακριβής σωματίδια, από αυτά τα οποία ήδη γνωρίζουμε, και ο τρόπος με τον οποίο τα ανακαλύπτουμε είναι πάλι παρόμοιος με τον τρόπο με τον οποίο ανακαλύπτουμε το Higgs. Δηλαδή, δεν μπορούμε να τα δούμε γιατί δεν είναι ορατά, απλά τα βλέπουμε μέσα από τα ποσά ενέργειας τα οποία εναποθέτουμε μέσα από τις διασπάσεις στους ανοιχτές. Άρα τώρα μιλάμε για πολύ ενθουσιώδης περίοδος που ξεκινάει στην αρχή και τα πειράματα. Οπότε μπαίνουμε στη διαδικασία σιγά σιγά οι επιστήμονες θα πάνε για τη σκοτεινή. Λοιπόν.
Άλλη μια ερώτηση για Σούση και μετά πάμε στις ερωτήσεις για τη ζωή του. Έλα.
How close are we to have a sushi?
How close?
How close? Same answer, we don't know. So, many of us think that supersymmetry, the lightest supersymmetric particle, might weigh between, let's say, 100 and 1,000 times the photon. So because we collide photons with a total of 10,000 times the energy of a photon, then that's enough energy, maybe, to make supersymmetric particles. And in particular, if the supersymmetric particles are going to make the dark matter, that's probably the preferred range of masses. But we don't know, we could be wrong. So we were thinking that maybe with the first run of the LHC, we were going to make supersymmetric particles.